familiar with the PDB archive probably know it has seen an exponential growth. So here we see the growth of entries in the protein data bank. We now have 120,000 structures. We're adding about 10,000 per year. And just recently, we exceeded the 1 billion atom mark. So it's becoming big data as well. And it's not just the number of structures that becomes large, it's the size and complexity. So here we see the scale of biology going all the way from small proteins all the way to a eukaryotic cell. And the largest structures in the PDB are now in maybe the 100 nanomolar range. So here we see the HIV virus, the HIV capsid. We actually have in our database contains 2.4 million atoms. And we actually have larger viruses. So for symmetric viruses, we have the Fausto virus with now 40 million atoms. And there are lots of advances now, especially with cryo-electron microscopy, where we will, in the future, may get giga-Dalton complexes within the next 5 years or so, and we want to be prepared for that. We also have growing complexity. We have all kinds of different shapes and molecular machines in the database. And the other issue is we have lots of users. We had more than 500 million downloads of our data files last year. We have more than 300,000 users coming to our website per month, so we need to take that all into account. So all those factors, the growth, the large user base, that together makes the PDB also now a big data problem. And what kind of problems do we see? First of all, users have problems displaying those large molecules. You cannot display them anymore. The network transfer is too slow, the I/O is too slow, parsing is too slow, etc., etc. So if you take a big structure like this virus, usually your browser will run out of memory or will just crash. That's kind of the bottom line what happens currently. And that's even worse if you work on a mobile phone. More than 10% of our traffic comes through mobile devices, and there you have even less resources. And finally, we're interested in being able to do large-scale analysis of the PDB archive, and we want to do that interactively. So you as a user, you draw a query, you run it across the entire PDB and get results back in seconds, not in hours or days. So that's the other part we want to address. And the way we do that is, first of all, for fast visualization, we do basically the same thing that YouTube or Netflix does. We compress our data, and then we send the compressed data to the client. So that solves that problem of fast visualization. And we can actually compress the entire PDB so much that we can keep it in memory on a server. So when a user requests a structure, it's served out of memory with very low latency. So we can really speed up this process. If I have time at the end, I'll give you a little demo. You can see how that works. Our other problem is large-scale calculation on the PDB scale. And again, we can compress the entire PDB and keep it all in memory. If we have a server with a compute cluster with multiple servers, we can have multiple copies. Every server can have their own copy of the PDB in memory, and that allows fast parallel computing on the PDB. Okay, you all know about 3D structures. As you know, in the PDB, we have proteins, nucleic acids, and carbohydrates. And they all have in common that they are polymers. So we have small building blocks, and that will help us in compression. So in particular, for those of you who are familiar with the details, generally the way 3D structures are stored is in a PDB or mmCIF file. It contains a lot of metadata, but then the real important information is the atom section, and a simplified version is shown here. Every atom in a protein, like let's say this Fausto virus has 40 million atoms. You have like 40 million of those rows here. And first of all, the information about, for example, this is the amino acid arginine. Those can be stored in a dictionary. We have 20 amino acids, so this can be stored once and not repeated over and over. We have numbers that repeat all over again, or letters that repeat all over again. We use run length encoding for that. And finally, we have data that vary slowly. Here we can compress them by doing delta compression, by only saving distant differences between values rather than absolute values. So that's really straightforward. The bigger problem comes with compressing the 3D coordinates, x, y, and z coordinates here. That takes about 70% of the space. So we'll show you what we do about 3D coordinate compression. So first of all, in a protein data bank file, the precision of the XYZ coordinates has 3 significant digits. So this limited precision helps us to just convert floating point numbers to integers by just multiplying them by 1,000. So that's step number 1. We can also do a lossy compression by just multiplying by 10. That basically means we're rounding it off at a resolution of 0.1 angstrom, and that's sufficient actually for all visualization as well as most calculation, because the experimental error is way larger than 0.1. And to see what the difference between lossy and lossless compression you see is down here. So here's the alpha trace of a protein. In green is lossless, in red is lossy. You can barely distinguish them. So for visualization, there's really no problem with that. And here you see an all-atom model. Even in the all-atom model, you can barely distinguish the two. It's more like for very specific purposes that you really need more precision than this. So this will obviously also help in compression. So first of all, we use some intramolecular encoding strategies here. And I will go through them. Intramolecular means within one protein chain. So we look at adjacent atoms. And we have 3 approaches. The first one we call delta encoding. We take the XYZ coordinates, which are in red here. Those are the absolute coordinates. We just take the differences between adjacent atoms, and that's called delta encoding. Now, the dynamic range of the deltas, obviously in green, is much smaller than the red one, so that means we need less space to store those data. The other approach we took is when you look at bonds in a protein structure, the bonds face in a particular direction. The way we can store it by taking each vector, we calculate a unit vector, and unit vectors can be efficiently stored by vector quantization, where we basically map a unit vector on a unit sphere, and we can store that as a single 16-bit or 32-bit integer. Then we'll store, we know what the average bond length is, and we can take the difference between the actual bond length and the average bond length, and we store this delta in bond length. And finally, this vector quantization has some error in it, so we need to store some delta x's, delta y's, and delta z's, which are the errors. That's shown here. The error is almost 0, but they're not always 0. Then we store the delta in bond length, and we store the unit vectors here. So that's a second way of compressing coordinate data. And finally, we thought about using methods that are being used for image compression. Since we're interested in lossless compression, we looked at this Legal wavelet, which is a lossless wavelet used in JPEG 2000 compression. So we applied that to the coordinates, and again, you see a nice reduction here in terms of the dynamic range of the data. Okay, so how well do those different methods do? On the left, lossless compression, you see those are the original floating point numbers. Then this is conversion just to integers already helps. They can be compressed more easily. And then the winner here is the intramolecular delta compression is doing the best here. For lossy compression, the intramolecular delta works well, and here the unit vector with 16-bit encoding seems to be the winner in this case. Okay, so there are other ways to compress data. About 10 or 8% of the archive, you don't have a single structure. You have multiple models, multiple conformations of the same protein. That's shown on the left. This is an NMR structure where you have maybe 20 up to 100 similar conformations. Again, we can use that idea for compression too. It doesn't work always, because in the 3 examples on the right, you can see there can be quite diversity in different conformation. That probably does not compress as well. But structures on the left, we should be able to use that for compression. And the way we do that is, instead of intramolecular delta compression, we do this between chains. We look at corresponding pairs of atoms and calculate the distances between them and just store the differences. And now, let's say we have an ensemble. To make it easy, we have just 4 protein chains, and we want to encode them with intermolecular delta encoding. There are different ways we could do that. We could take the first protein chain as a reference and calculate the deltas to all the other ones. Or we could do what we call the waterfall model, where you store the deltas between subsequent chains. Or finally, maybe that seems to be the most sophisticated model, that you create a graph where we have different way of weighting the edges, for example, by RMSD, by the average delta, or by just G-zipping the differences. And so if we have weights, we can then run a minimum spanning tree calculation and find basically a graph that connects all those points with the minimum weight, basically achieving maximum compression. Okay, so here are the results for lossless. We see that the intermolecular delta using this waterfall model, for example, does only slightly better than the intramolecular compression. We only save like 7%. For the lossy compression, however, we do save a little more. In terms, the intermolecular delta saves 18% compared to the intramolecular delta. So here we gain a little bit, not very much. So there's a third way we can think about compressing 3D data, and that has to do with symmetry. Usually proteins don't come alone. You have multiple copies of them in what's called the asymmetric units. For example, in this case, there are 5 copies of the same protein. They're not exactly identical, but they're very similar to each other, similar to the NMR structure I showed you before. Again, we can superimpose those copies onto each other and then calculate the intermolecular delta. For the case of an asymmetric structure like the HIV capsid, although there are more than 1,600 copies here, but they are very similar to each other. Again, we can use the intermolecular delta encoding for those situations, and now we're saving much more. So for lossless compression, we now save 44% compared to intramolecular delta, and for the lossy, we save much more, 60%. So this works actually quite well. Okay, so here's a little summary. So we have 2 options to encode coordinates, either intramolecular, or if we have multiple protein copies, we can use intermolecular encoding. But the last 2 cases I showed is only a small percentage over the all archive. So if we see what do we gain through intermolecular delta compression, it's unfortunately only 7%. So it was a little bit disappointing, but nonetheless, we decided to just use intramolecular delta encoding. Overall, it works very well. It's the simplest algorithm you could possibly think of, so it's very fast in terms of speed and simplicity. So basically, we delta encode adjacent atom positions. We then use those data to compress or pack them as 2-byte integers using some recursive indexing algorithm. And finally, we gzip those data because we need to support that to browsers, and most browsers support gzip and unfortunately not more sophisticated compression method. And then my colleague Alex found this quote here, which really summarized what I was talking about, and it says, complex code fits neither into processor caches nor into programmer's mind. It is thus prone to be slow, faulty, or not widely implemented. So that's kind of basically our strategy. We want to keep it slim and fast because we want people to adopt this. If we make it too complex, it may go nowhere. Okay, so now we have a compression strategy for the PDB. Now we need to package that into a file format that people can use. We call this mmCIF, Macromolecular Transmission Format. And the basic idea is the same, what YouTube or Netflix is doing. They compress their video files and serve that. We serve molecular structures in this compact mmCIF format that allows fast network transfer. It allows in-memory computing on the entire PDB. It can be parsed extremely fast, which we need for interactive visualization, but also for large-scale mining. In addition, we have a completely self-contained data model that contains more information that's currently in PDB or mmCIF files. We have complete bond information and bond order information in there of all ligands of all the molecular entities. And the way we package this, rather than inventing our own file format, we're using message pack, which is a binary container. It's basically like JSON, but it's binary for very fast parsing. And finally, it's interoperable because message pack is available in more than 50 programming languages. So here are some applications, some benchmarks. On the left, that's the size of the PDB in mmCIF. gzip compress is 30 gigabytes. If we lossless compress it using mmTF, we go down to 7 gigabytes, so this is lossless compression. If we do the lossy compression that I talked before, we can actually go down to 800 megabytes, so it's pretty astounding. Now what you can do, all of this now easily fits even into the memory of a laptop. You can do PDB-wide calculation, have random access to any structure in microseconds, basically. But what's more important than compression for us is speed. So if you parse the original mmCIF files on a Mac mini computer, for example, that will take 400 minutes. Using mmTF, we can do that in less than 2 minutes. So it's basically, you can almost interactively run through the entire PDB. Okay, here's a simple example how we use that. We want to find all C-alpha contacts within some distance range within the PDB. The naive approach would take 400 minutes, so it's an overnight job. Then we think about, oh, we can do some geometric hashing, speed it up. It barely does anything, gives you a 10% improvement. But then if we use mmTF, you see we go from 50 minutes to 6 minutes. So basically, this is an I/O-bound process, basically. A lot of the analysis we do on the PDB archive are I/O-bound, and that's how we get this dramatic speed up here. So the other use case I was talking about is really, we call this the Macromolecular Transmission Format, because we want to be able to transmit large structures to web browsers all over the world. We need to do that fast. That's why it should be small. So the best case scenario is obviously if we're in San Diego, our offices are 1 mile away from the San Diego Supercomputer Center. Best case scenario, taking the 100 largest structures in the PDB, downloading them in a Chrome browser using JavaScript. We can do that in San Diego in 36 seconds. Using mmCIF, that would take 800 seconds. If we ship the data across the US to Bethesda, again, this takes 85 seconds using mmTF and 2,400 seconds using mmCIF. So we get about a 30-fold speed up there. We can even ship it all the way to Japan about the same time as we ship it to the East Coast. And numbers in Europe don't look quite as good. But in Russia, basically, mmTF, again, pretty good transfer rate. And mmCIF actually failed because it has too much client-side overhead. Your browser just crashes, so that's what happened there. Okay, I'm running out of time here. So here's a summary. The Macromolecular Transmission Format is a binary compressed format for efficient visualization and large-scale analysis. We reach like 10 to 100-fold speed-ups in various applications. All the software is available open source. The data mmCIF files can be downloaded using RESTful web services, and we also package mmTF in big data format, such as Hadoop sequence files, which can be used with big data frameworks such as Hadoop or Spark. And then finally, I want to acknowledge the PDB team. I want to acknowledge the NIH and the BD2K effort, and I want to also thank our early adopters, which are both commercial companies, various bio projects, and various JavaScript-based viewers. And I take any questions. And while I'm doing the question, I'll give you a little demo how fast we can download the largest structure in the PDB, which is 3J3Q from San Diego. We can load that hopefully within seconds here. We'll see if it works. Yeah, so here's the HIV capsid. That's just the data, retrieved from San Diego. And basically any other application would take maybe minutes, hours, and probably just crash at the end. So any questions?